Okay guys, thanks for coming along today. I'm Terry McBride. I'm from Parramatta Climate Action Network, and we're going to do a climate change presentation today. This has come about because we realised people were going to climate change presentations and they weren't really coming out much wiser than when they went in. So Parramatta Climate Action Network developed this talk, and we're going to do a physical demonstration as well. We all have a right to clean beaches. We have a right to a clean ocean. We have a right to protect our wildlife. We have a right to look after our neighbours. We have a right to clean air. We have a right to proper environmental regulation. And that's so we got a lot of places for our kids that it's nice and clean to go swimming in. There's nothing like the feeling of clean sand between the toes. So somewhere along the line, we've missed out what's really going on. These things are not rights, they're responsibilities. There's a big difference between a right and a responsibility. One of the biggest problems with getting the message across about climate change is a day exactly like today outside. It's nice and sunny, there's clear blue skies. You look up and you see this endless amount of blue. And it just looks impossible that someone as small as us, as individuals, could affect the makeup of that of the atmosphere, that we could affect the workings of the planet. What we need to realise is that our atmosphere isn't that big. We're very, very wide. We're in diameter, we're 12,756 kilometres, but the usable part of our atmosphere is only 11 kilometres. This is the makeup of our atmosphere here. It's the ionosphere, the metasphere, the ozone layer, the stratosphere and the troposphere. Now, where the troposphere meets the stratosphere, that's called the tropopause. And on average, that's about 11 to 14 kilometres from the surface. The tropopause is not a fixed line like on the photo just there. It moves up and down. It can be as low as 6 kilometres and as high as 24 kilometres. And the troposphere is where most of the carbon dioxide in the atmosphere hangs around, okay? A carbon dioxide molecule is slightly heavier than an air molecule. So it mainly hangs around in the troposphere. There is carbon dioxide in the stratosphere, but most of it is in the troposphere. Now, 11 kilometres from the ground to the tropopause. I drove 3 times that distance today to get here. So it's not far. It's just that when we walk outside and look up, we think, well, it's absolutely massive because it looks absolutely massive, but it's not. So this is an amazing photo from the space station, and this actually shows the layers of our atmosphere on the space station. And if I was going to show you on this balloon here, how thick our atmosphere is, then it would be that thick. That's how thick our atmosphere is. Okay? So could we change the chemistry makeup of the atmosphere? Yes, we can. Okay? No, I'm not running for President of the United States. Okay? Could we change the chemical makeup of the atmosphere? Yes, we can. It's paper thin. So how does global warming work? Well, what happens is that you have incoming sunlight, and that's called shortwave radiation. So that's a short wave. It's not as long as long wave terrestrial radiation. So that's the long wave, and I'll show you why I'm holding these up shortly. So you have shortwave solar radiation coming in from the sun. It hits the atmosphere, and about 25% of that shortwave solar radiation is reflected back from the atmosphere back out to space. About 75% of it makes it through the atmosphere and hits the Earth. About 3% of that is reflected back into space by the ice and the snow, and about another 25% is reflected back by the Earth, and then the rest of it heats the planet up. If you go out there today and you walk on the asphalt in bare feet, you'll burn your feet, right? Okay, that's because that surface is absorbing that shortwave solar radiation, but then what it does is it re-emits that heat back out. as the day moves on and we start getting into evening time, it re-emits that heat back out from the ground. And when it re-emits that heat back out, it re-emits it out as long-wave terrestrial radiation.
Well, hi guys. I'd like to demonstrate for you a very simple demonstration that could be done in a classroom setting or have students do it at home. This actually comes from the National Weather Service learning lesson, one of the NOAA websites. So you start with 2 clear soda bottles and partially filled with water. I filled them about halfway with water. And you need to have a stopper. I use the rubber stoppers I got from chemistry lab, but you could use even a piece of clay or a piece of tape over the top. Then you want to have a thermometer for each. Ideally, you could use just a plain glass thermometer, sit in there. Or I like using these digital vernier GoTemp, which I can just monitor on the computer, and that's what I'm going to do. So then you need a lamp, a heating source. And the idea is that one of them, we're just going to put the stopper on it, and we'll stick the temperature in here, the probe in there, and now it will record the temperature of the gas in there. Now the second one, we want to develop some CO2 in the bottle to see the effect on the temperature, change in temperature of the atmosphere as it's heated. So what we're going to use is these Alka-Seltzer tablets. I bought the cheap ones from Walmart, but they should work fine. And so I'm going to stick them in there, and they will effervesce, and they will. Okay, hopefully you can see that. Now I'm going to put the stopper on here, and I'm going to stick my temperature probe. Okay, tight, and now I'm going to turn the lamp on, and I am going to observe the temperature for an hour. I'll just come back in an hour. I will shut this video off and turn it back on, and we'll see what the effect of the temperature of the gas in each bottle is. Stay tuned. Well, welcome back. It's been almost an hour. This this demonstration is about over. You didn't need to wait an hour, but my temperature change for the approximately 40 centimeters that I had from this light bulb to these bottles was 9 degrees Celsius, warmer in the bottle with the CO2. Obviously, that is the carbon dioxide is having an effect. Variables in this obviously would be the wattage of your light bulb and how close you are to it. But I think the point is very easy to demonstrate with very simple equipment. Students could do at home, but I think it'd be very effective to do at the beginning of a class or a lab, and then at the end of the class, even a short class. And this is stuff that's readily available. I bought the Alka-Seltzer from Walmart. Good luck.
Okay, so that's one of the problems when we do a climate change talk is people walking away understanding exactly what the role of carbon dioxide is in the atmosphere. How does it capture heat? Okay, and pretty much I've never seen a climate change present. So that's one of the problems when we do a climate change talk is people walking away understanding exactly what the role of carbon dioxide is in the atmosphere. How does it capture heat? Okay. And pretty much I've never seen a climate change presentation that explains that. So what I'm going to do is I'm going to pretend I'm a carbon dioxide molecule here. So I'm 1 part carbon, 2 parts oxygen, okay? And I'm up in the atmosphere, and all molecules have molecular motion, okay? So I'm up hanging around in the atmosphere like this, okay? I have movement and I have a frequency that I move at. And so that's what that looks like, okay? And then what happens is that when something comes up and hits me with energy, I absorb that energy. I speed up. The same way as like water molecules, if you're heating up water in a kettle. The molecules start out like this and then they get like this, okay? So it's the same thing. So what we're going to do now is we're just going to demonstrate how that works in the atmosphere. Okay, guys. So this is the red arrow here is shortwave solar radiation. So that's the sunlight that comes down from the sun, and that's in the visible part of the light spectrum. And the yellow one here is long wave terrestrial radiation, which is the heat energy going back out from the Earth, which carbon dioxide carries, and it's a different frequency to the shortwave solar radiation. So what I'll get you guys to do now is with your shortwave solar radiation arrows, I'll get you to walk straight at the planet here, and we've got our two ladies here who are going to pretend to be carbon dioxide molecules, and they're going to be there moving in the atmosphere. And if you walk into them, I want you to turn around and walk back. And if you miss them, I want you to keep walking through to the planet here. So just walk in a straight line towards the planet. Okay. Some of our solar radiation, when it hits the Earth's atmosphere, it gets reflected back out to space. And some of our shortwave solar radiation makes it through to the planet, and it warms the planet up. So what I'll do is I'll get you guys to drop those arrows down there, and you guys can drop the red ones and pick up the yellow ones. So come over here and pick up the yellow ones. Okay, so what happens now is the shortwave solar radiation has got through, it's warmed up the planet, and now the long wave terrestrial radiation will be going back out, which is close to the frequency of the carbon dioxide. So what happens now, I want you to walk straight out from the planet there, and when you walk out, if you hit the carbon dioxide, just turn around and walk back, and if you miss them, keep walking. Okay, that's our carbon dioxide has captured that heat there coming out from the planet, and some of it has gone back out to space. So that's the normal natural carbon cycle. So I'll get you guys to walk back across to here. Now we're going to add in our man-made carbon dioxide. So I need two guys to come up. Okay, great. And I'll get you to stand here and you to stand just there. Okay, so we're all moving with carbon dioxide in the atmosphere. Okay, so we've added in our man-made carbon dioxide now. And I'll get you guys to walk straight out from the atmosphere, and if you walk into that molecule, turn around and go back. Okay, so as you can see, we've captured a lot more heat energy going back out from the planet there. And that's just the rough science of how carbon dioxide works in the atmosphere. Okay, thanks a lot for your help, guys. Thanks. We've got long wave and short wave. Okay, so the short wave is in the visible light. That's the wavelength, that's how long it is. That's the frequency that it moves at, and that's the amount of energy that it carries. Okay, so that's the short wave radiation coming in. And then we've got the long wave terrestrial radiation going out, which is in the infrared part of the spectrum. So that's the length, that's the wavelength, that's the frequency, and that's the amount of energy that it carries. There are two different wavelengths to do with why the planet is warming up. And carbon dioxide doesn't really capture the wavelength in the visible wavelength because it's a different frequency to the movement of the molecule. Whereas the infrared frequency is pretty much the same frequency as the carbon dioxide molecule. Okay, and that's why it's able to capture that energy. So can small amounts of invisible stuff make a big difference? Well, it did for this lady here. She didn't put any sunscreen on, but a friend put some on his hands, he put them on her back, and so you can see where she didn't get burnt. Okay, that's small amounts of invisible stuff making a big difference.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera which is purring away here, and a candle, this glass tube which is hooked up to this rather large canister of carbon dioxide gas. Now if I light the candle, you'll see that on the monitor the camera picks up the flame perfectly. Look at that, the hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide. Just keep your eye on the flame. The gas is invisible, so you don't see it fill in the tube. But as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat. The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube. That's exactly how carbon dioxide works in the atmosphere. It traps heat, preventing it from escaping into space.
A lot of people seem to think that it was actually discovered when Al Gore turned up on the scene. And I don't know why that is. It's probably something to do with the media, but we like to call it before Al Gore science, okay? It was discovered a long time before Al Gore, or bags. So wherever you see bags on one of the future slides, that stands for before Al Gore science. And it means that the science that I'm showing on that slide was discovered a long time before Al Gore. So we first found out about it in the 1820s. A French scientist, Joseph, he started doing experiments to work out why that the planet stayed warm, why wasn't it cold. And he worked out with very crude methods that some of the gases were able to actually trap heat. Then in 1959, John Tyndall really made the major discovery of that gases could actually trap heat rays, is what they called them then. They didn't know about the different parts of the spectrum. And then that was followed by Savanti, who was intrigued by how the ice ages worked. And he realised that there had to be something that caused the melting of the ice ages. And so he identified CO2 as a key contributor to that. Then in 1938, this guy wasn't a scientist, he was actually an engineer, but he had a great interest in science. He worked out on flimsy grounds that a doubling of CO2 would bring about a 2-degree rise in temperature in the future. But of course, back in 1938, he was actually thinking a couple of centuries into the future. So a long time. And then in 1970, James Lovelock and Lynn Margulis introduced the Gaian hypothesis, which explains that the Earth is a self-regulating living organism, and that's called a biosphere. So a biosphere means that the land and the air and the ocean all interact with each other to keep the Earth in a habitable state for us. And the great thing about a living organism is that you can kill it. How long have we known about this stuff for? This is my friend Sue. She was throwing out her old school books, and so I was having a read through her geography book. And I couldn't believe my eyes. So this is her geography school book from 1981, year 8. And it says, and I quote, "Trees and plants give us oxygen to make the air fresh and clean. The rainforest has more plants in it than any other parts of the world. Consequently, as the rainforests get cut down, we will have more carbon dioxide in our air. This could easily change our climate and environment." End quote. So that's from a 1981 school book. We used to teach it at school. So one has to wonder what the problem is with accepting the science of climate change today. Another problem that we have with climate change talks or with the media is peer-reviewed science. So peer-reviewed science is an academic process, and the idea is to verify someone else's work to make sure that they're not making unsubstantiated claims without evidence. And so that's what happens here. The articles get put in, they're peer-reviewed by people who are experts in the same field. They either accept it with revision or they reject the work. The first example of peer-reviewed science was in 1665, so it's been around for a long time. And the method that we pretty much use today has basically come from the Royal Society of Edinburgh in 1731, and the peer review process has pretty much evolved since then. So it's got quite a long history. When we look at science and that, and if we want to find out what's going on, we should look at who has the peer-reviewed science and who doesn't have the peer-reviewed science. So does peer-reviewed science matter? Yes, it stops people from making improper assertions like climate change is all crap. It helps scientists with their methodology and process so that it can be improved, and the science can continue to build on the already known science at the same time reviewing the science that's already known. So that's why we have a peer review process. So these are some of the gases that are up in the atmosphere that help capture heat, and there are only tiny amounts of gas, what they call trace gases. A lot of them are measured in parts per billion, not parts per million. They're only tiny amounts. And so this is our atmosphere up here. So 78% nitrogen, 20% oxygen, and then the rest is made up into this little part here, not quite 1% of the Earth's gases in the atmosphere. If we have a look at that, if we take that 1% and we break it down, CEFCs make up about 6%. They last quite a long time in the atmosphere, and they're about 11,000 times more effective at capturing outgoing long-wave terrestrial radiation. Then we've got nitrous oxide. So nitrous oxide is once again a very powerful greenhouse gas. Nitrous oxide and methane, since pre-industrial levels, have risen 17% in the Earth's atmosphere. Methane and nitrous oxide are quite effective greenhouse gases. They last quite a long time in the atmosphere. Methane lasts about 9 years, and then it oxidises and breaks down into carbon dioxide. And then carbon dioxide lasts about 30 years. So these are only trace gases. They're either measured in parts per million or parts per billion, but they have a big effect. So what is the concentration of CO2 in the atmosphere? When we go out in the street, we talk to people at street stalls about climate change all the time, and they come up to us and they walk right up to us and they're really angry and they say, it's 0.0395% of the atmosphere. It's so tiny it couldn't make a difference. And we go, it is. And they go, but it's 0.0395% of the atmosphere. And we go, it is. And this is bags as well. It's basic mathematics that's been around forever. 1% is 100th, 0.1 is 1,000, 0.01 is 1/10,000, 0.001 is 100,000, and 0.001 is 1/1,000,000th. So 0.039% is 395 parts per million of carbon dioxide in the atmosphere. The reason why we measure it in parts per million is because it's an easier number to understand than trying to go around and calculate or talk to people about a tiny amount of gas saying 0.0395%. So we make it in a more understandable number, an easier number that we can calculate, which is 395 parts per million. So if you look at a can of soup when you get home, on the can of soup it'll have about 220 milligrams of sodium in it. Okay, it doesn't say 0.22% sodium. It says 220 milligrams. Okay, they're just easier numbers for us to understand. So what's the concentration in the atmosphere? 395 parts per million right now, today, and we're heading up to 450 parts per million. We'll hit that at the current rate of increase in about 12 years from now. So 12, 13 years, we'll hit 450 parts per million. What we've got to do is we've got to get back down to 350 parts per million as fast as we can. Okay, so 350 is a good number, 450 is a bad number, and we're at 395 now and going up. What's the biggest greenhouse gas in the atmosphere? It's water vapour. How could this be? It's science that's been around for a long time. So when you add heat to the planet, it causes the rate of evaporation to increase, That puts more water into the atmosphere. When you've got more water into the atmosphere, it's able to absorb more heat energy. So you're basically putting more energy into the atmosphere. So the more you warm it, the more water evaporates, the more energy you can hold in the atmosphere. And so this leads to more extreme weather events. How much has the average temperature increased so far? Since 1750, we've gone up about 1 degree Celsius. So my mates say to me, well, 1 degree Celsius, it was 10 degrees when I got out of bed this morning, it's 20 degrees now, that's 10 degrees difference, so 1 degree is no big deal, okay? Well, 1 degree is a big deal. What happens is that we've had the Arctic sea ice melt, the volume of that ice is decreasing, and so it continues to decrease. With that ice melting, it causes problems with our ocean conveyor belts. It causes problems with the animals and stuff like that in the Arctic. There's ocean acidification that's happening right now. There's more extreme weather events. There's desertification. There's biodiversity loss. So this is just with 1 degree rise. If we can't deal with a 1 degree rise, what are we going to do when we get 2 degrees? So 450 parts per million represents an average Earth temperature increase to 2 degrees Celsius. Back in 1760, Jonathan released a paper called photometria, and that's about the reflective ability of surfaces to reflect shortwave solar radiation. And that's bags. This diagram here shows us the different reflective abilities of different surfaces to reflect that solar radiation back out to space. So as you can see, everything has a different ability to reflect light. There's a couple of funny things in there. One is if you go out and look at new housing developments, there's lots and lots and lots of dark tin roofs. And of course, so what we did was we cleared the land to build the houses there. And so if it was grassland, it had a 25% ability to reflect that light back out. But if we build the house on top of that grassland and put a dark roof on it, we're absorbing more of that energy rather than reflecting it. So if you get massive housing developments that are covering acres and acres of land, you're now absorbing more energy than you were reflecting before. But the really important one here to look at is the snow and ice, because the albedo effect is part of a positive feedback loop. What happens is that you add carbon dioxide into the atmosphere. That causes the planet to warm a little bit, which causes the ice to melt. And when the ice melts, it exposes more dark ocean, more dark water, and more dark land. And when it exposes this ocean and land, it's able to absorb more energy. It's a dark surface, not a light surface. So this is the Muir Glacier in 2004. That was it in 1941. Okay, and that's actually retreated further back than that now. But in the meantime, all this area here now is absorbing all that energy that it was reflecting before. The same with the land, all up there, that's all now absorbing all that energy, which causes more warming, which causes more ice melt, which causes more exposed dark ocean or land or lake, which absorbs more energy, which causes more warming. That's called a positive feedback loop, and that is definitely kicked in now around the world. So it's not just glaciers, it's the Arctic sea ice. Last year was its biggest melt ever. So which one collects more heat? Is it the oceans or the land? It's the oceans. Right now, the ocean is currently collecting 4 Hiroshima bombs a second of heat energy. So in the last decade, our temperatures have sort of stabilised. We haven't got year-on-year record average Earth temperature increases. That's because most of that energy has been absorbed by the oceans. It's much harder to heat the water than it is to heat the atmosphere. And currently right now we're absorbing all that energy into the ocean. It's about 4 Hiroshima bombs a second, or about 360,000 Hiroshima bombs a day. So what happens here is we've got the ocean conveyor belt there. It's super complex, so I won't go into much of it. picks up the heat in the tropic areas, it transports it up, it releases that heat as it's getting up towards the Arctic, and then when it hits the Arctic, because the top part of the water has been evaporating, it's salt heavy. When it hits the cooler waters and the ice and that, it cools quite quickly. It's dense with salt, so it drops to the bottom of the ocean, and then that pushes the water along the bottom, deeper, colder parts of the ocean conveyor belt. Okay, and that's pretty much how it works. Now, as we lose that ice off Greenland and the Arctic sea ice, and that starts to warm up, this ocean conveyor belt will weaken. Now, that won't just be bad news for Europe. It'll have ramifications around the world if that conveyor belt weakens. So there's no scientific evidence of that yet, but it's early days, so stay tuned. So the other CO2 problem, this is hardly ever mentioned. The reason is because it's so complex. It's ocean acidification. It's incredibly complex science, so people tend to skip over it, but it is becoming a problem now. We've gone up 0.1 on the pH scale since 1885, and we are actually are drawing more carbon dioxide into that ocean now.
Marine pteropods, or sea butterflies, are found throughout the ocean and are a major food source for fish and other organisms. In laboratory experiments, this pteropod shell dissolved over the course of 45 days in seawater adjusted to an ocean chemistry projected for the year 2100. What changes in the ocean might be putting pteropods at risk? The burning of fossil fuels has caused levels of carbon dioxide in the atmosphere to rise. This carbon dioxide, or CO2, doesn't just stay in the atmosphere. Roughly 30% of it is absorbed by the ocean. When CO2 reacts with water, it forms carbonic acid, which quickly releases a hydrogen ion, or H+. The more hydrogen ions, the lower the pH, or more acidic a solution is. As CO2 levels increase over time, seawater will progress towards the acidic end of the pH scale, a process called ocean acidification. We can make projections of this change in the ocean pH over time. It is expected that later this century, if CO2 emissions continue at the current rate, the average pH of the ocean will drop from 8.2 to 7.8. This relatively small decrease in pH may not seem significant, but it could impact many species of marine life. For pteropods, corals, and other species that depend on shells and exoskeletons, ocean acidification will lead to a decreased availability of dissolved calcium and carbonate, the chemical building blocks they use to make their shells and skeletons. If ocean chemistry changes as expected, shells with calcium carbonate mineral structures may begin to dissolve, depending on where they live in the ocean. How do we know that ocean acidification is happening? Scientists at NOAA and across the world have measured these chemical changes over the past 40 years during research cruises, taking hundreds of thousands of ocean water samples. Shown here are the results from cruises in 1991 and 2005, where the availability of the shell mineral was sampled. In both years, the highest concentration of available shell minerals were found in the surface waters as shown by the dark yellow colors. Deeper waters naturally have very low availability of these minerals. However, when we look at how these values have changed between 1991 and 2005, we see that the availability of the shell mineral decreased much more in the surface waters, as indicated by the blue colors. In other words, ocean acidification is impacting shallower areas much more than deep areas. Shallow waters are where the bulk of the ocean productivity occurs, including the most diverse and economically important species and habitats. And these changes aren't occurring in just certain parts of the ocean. They're occurring throughout the entire ocean. Today, repeated research cruises and permanent sampling stations continue to monitor changes in pH and availability of calcium carbonate minerals. As the ocean approaches a critical transition between shell building and shell dissolving, food webs in the world's oceans could be impacted. Phytoplankton and zooplankton, like pteropods, form the basis of most oceanic food chains. Coral reefs form the foundations of the most diverse marine habitats, and shellfish, such as oysters and crabs, and finfish, such as salmon, support economically important fisheries in many of the world's coastal communities. People depend on the viability of these species to ensure a healthy future of our own.
So it's not looking good for us. But wait, there's more. Microscopic plankton also photosynthesizes. So when the carbon dioxide mixes with water through wave action, the plankton latch onto that carbon dioxide and they keep the carbon and release the oxygen as a byproduct. So 70% of the world's oxygen comes from the oceans, from microscopic plankton. If we keep acidifying the ocean, we're going to reduce our ability to have that oxygen production. And it's important that people get the message that there is a problem around it. What do scientists disagree on? So it's called climate forcing or climate sensitivity. So what happens is the media all the time will report that the scientists are arguing over climate change, but they're not. They're arguing over climate forcing or climate sensitivity, and what they do is they just change that word in there from forcing to change. So they say the scientists are arguing over climate change, they're not. So the forcing is the amount of radiative energy coming into the earth and the amount that's leaving. When it's a positive number, it's a positive forcing effect. When it's a negative number, it's a negative effect. So they've calculated that the human action on Earth is a positive climate forcing. So we're changing the climate. It's just the rate, the speed of which the climate is changing, or the different sensitivities that different ecosystems have to that change. So what's wrong with scientists? Why aren't we getting the message? Well, it's the way that they talk. As you can see, they talk completely differently to how I talk. So some of the things that they like to say is the greater probability, the likely range. Most of the key vulnerabilities to the climate change are related to a climate phenomena that exceeds threshold for adaptation. So if you said that to my mates, they would pass out. You know, most people are like that. They don't understand that language. So scientists need to change their language in order to get their message across better to ordinary people like me. The other thing is the carbon cycle, the only cycle in the Earth's systems. Do any of you guys know? No? Okay. There's a water cycle, there's the carbon cycle, there's sulphur, phosphorus and nitrogen. And they're all cycles, that all elements that cycle through the Earth system to keep the Earth in a habitable state for us. A better way to describe it is that at least 3 of these cycles are obese. What we're doing is we keep adding to them. With carbon, we keep adding carbon dioxide. With phosphorus, we keep adding fertiliser to the natural phosphorus cycle. So we keep adding to these things. Nitrogen is another one that we keep adding to. Sulphur is another one. Okay, so when we burn fossil fuels, we get sulphur. So it adds to the natural sulphur cycle. And when you keep adding stuff to it, it has a negative effect. So for instance, weeds might proliferate because they weren't able to get a hold because there wasn't the availability of the element or mineral that they needed. In the oceans, it might be jellyfish or some sort of coral-eating starfish or something, because we've added the nutrients to the water. They've now got more nutrients, so they proliferate and they upset the balance of the cycle. And that's what we're doing. In all those cycles, we've upset the balance of those cycles. One thing I want to make clear to all you guys here today is that all life on the planet is totally dependent on the natural world, today and in the future, okay? You guys need to understand that, because we grow up in the cities and we want food, we go to the supermarket to get it. If we want water, we go to a tap. So we've lost that connection with the natural world, and we are totally dependent on it for our survival today, now, right now. No matter how big our egos are, no matter how good engineers we are or scientists we are still today totally dependent on the natural world for our survival. Here's some of the free services that we get from the natural world every single day. This is just some of them. There's a really important one up there. Does anybody know what percentage of Australia's agricultural crop depends on pollination? Does anybody know today? Yeah, that's pretty good. Yeah, it's 60%. So if you guys listen to the news, you'll be noticing that there's a bit of a bee crisis happening right at the moment. Bees and other insects are very important pollinators to us, and as climate change is happening, that's affecting those species, and so we've got less pollination happening. So we're going to lose our ability to grow food. That's going to be very bad for us in the future. It also affects our clean water, because the natural world cleans our water for us. So we've got water to drink, and then we've got all these other really important things: disease regulation, pest regulation, water cycling, primary production is super important for us to survive, knowledge systems, food, fibre and fuel. All these things nature gives us for free every day, but we don't count them when we do financial. Okay, they're called externalities. We don't count them into our finance, but we should, because they're really important. And of course, the best one, of course, is inspiration. So that's why I'm talking to you, because I'm inspired by the natural world to tell you that it's in trouble. We've got to pull CO2 out of the atmosphere quick smart. There's two main ways of doing that: the ocean ecosystems and the land. We'll talk about carbon capture and storage. Just yesterday, Obama announced new laws they're bringing into effect in the US about carbon capture and storage. So any new coal plant now that's built in the US, they have to be able to separate the carbon dioxide and store it underground. That's the rules. Everybody knows that this technology is not available. It won't be available for at least 20 years, if ever. So effectively what he's done is he's priced coal out of the market. Nobody will be willing to back coal from a risk management type of deal with carbon capture and storage on it. Storing carbon underground is not a good idea. Nobody's ever been able to get it to work. So what we should do is just try our traditional method of planting trees. High-tech stuff. It's new technology, but let's go out there and plant some trees, okay? So we know how to do it, we know what it does, and we know that it draws down carbon dioxide through photosynthesis. So trees are our carbon capture and storage units, okay? We've cut down 60% of the trees since 1750. So that's a pretty big number, isn't it? Around the planet, we've cut down 60% of all trees since 1750. Does anybody believe that number?
It's probably more.
Yeah, it could be, but we'll go for 60. We'll stay pretty middle of the road, okay? And so yeah, it's a pretty big number. It's hard to believe, but these are two images here. So the top image is of Victoria before pre-European settlement. Okay, and the green part, of course, is the vegetation. And of course, you can see the bottom part of New South Wales there. This is off a government document. I can't give you one for the world because there isn't one. So I've just used these ones as an example, but we're pretty typical Western country. We like cutting down trees and ruining our environment. So we're no different to anybody else. As you can see, there's a dramatic deforestation there. So we've lost all that ability to draw down that carbon and release oxygen. So what do we need to do? We need to protect old growth forests. We need to start planting trees as a national priority. We need to revegetate, bring in sensible forestry management programs. We fix river systems and we stop polluting the oceans and expand marine parks. Pretty much we've just voted in a government that's doing the opposite to nearly all of those. So, but that's pretty much what we need to do ASAP. With deforestation around the planet right now, whatever we deforest, we're only replanting about half of it, okay? We're not replanting all of what we're deforesting. Now the problem is when we replant half of it, we only replant the tree. When you go and deforest an area, you don't just cut down trees, you cut down the community. When you go and reforest an area, you only plant a tree. You don't replant the community. So you've lost a lot because the community, it holds all sorts of things. It holds biodiversity, it holds carbon. When you get rid of the scrub, you normally burn it. It puts carbon dioxide straight back into the atmosphere. The soil around the area releases its stored carbon from the soil. Okay, so you've lost a lot. Okay, so every good climate change talk has its scary part, and this is my scary part if you haven't been scared yet. So this is a time frame, and you read it from the bottom up, not the top down. So they're the years there, and the numbers of parts per million of carbon dioxide in the atmosphere are accurate in those years right up until now, which is 2013. So this is a social comment on this side, and this is what actually happened in that year. In 1980, the National Academy of Sciences reported that it's highly credible that a doubling of CO2 will bring about a 1.5 to 4.5 degree rise in average Earth temperature. Then in 2001, the third IPCC report effectively ended debate, all but a few scientists, about whether or not we were causing climate change. So we've passed all of the worst case scenarios from the 2007 IPCC report. So I remember back in 2007, that's when I started out as a climate campaigner, and the media absolutely went to town on their worst case scenarios, saying that they'd never happen for 100 years. We've already passed all of them. Okay? So from there up, at the current rate of increase of carbon dioxide into the atmosphere, we'll hit 450 parts per million in about 12, 13 years. That seems like a big jump to a lot of people, but what's happening is as our ecosystems are degrading, they're losing their ability to draw that carbon dioxide down. So it's staying in the atmosphere. So it's increasing faster than what it was before. So it only used to increase about 1 part per million per year. Now it's up to about 3 parts per million per year. And that will increase in the next decade. So we'll hit 450 at about 12 or 13 years. And of course, this is only one possible future if we choose not to act. So that's not set in concrete yet, but we have to get out there and we have to act now. So there is a solution, and here's the good part to the bad part. This one here is concentrated solar thermal for stationary energy. So stationary energy is our biggest emitter right around the world. It's 40% of all our carbon dioxide emissions. And this here is a zero emissions technology. It makes power 24 hours a day just from sunlight, because it's able to store the energy during the day and then dispatch that energy at night time from those big tanks there. There's a group, a not-for-profit group out there called Beyond Zero Emissions, and they've developed a plan to make Australia 100% renewable energy. It's about decarbonising all parts of the economy to get as much carbon dioxide out of the atmosphere as fast as possible. So there's the plan there for stationary energy. It's 23 wind regions, 12 solar regions plus a grid upgrade. That comes to $370 billion or $37 billion a year for 10 years. Which is 3% of GDP. So for a rich country like Australia, it's easily affordable. We can easily do this with simply choosing not to. So has anybody here had an accident not for 5 years? Anybody here? Yep, okay. You haven't had an accident for 5 years, do you still insure your car?
Yes.
You do, why?
Protection.
Yeah, for something that may or may not happen in the future. Okay? That's why we take out insurance. So in society, there's still a lot of debate about whether climate change is happening or not. But if we're sensible, reasonable people, in the face of uncertainty, what we would do is we would take out insurance against that being a possibility. Okay? So if you want to know what insurance looks like, this is what it looks like here. Okay? That's what insurance looks like. No letters, no numbers. That's what insurance looks like. Okay? So in the face of uncertainty, what we do is we take out that insurance to prevent what may or may not happen in the future. So what we do is we build renewable energy now. We have a plan to do that. It's as a matter of fact, BZE is not the only plan out there now. There's 2 other plans out there now to make Australia 100% renewable energy. We transition away and sensibly from fossil fuels. This does not mean that we shut down fossil fuels overnight. we plan a transition away from these fossil fuels over 10 to 15 years. Okay, we still need the power to build these pieces of infrastructure, so we just can't shut down fossil fuel overnight. So we need to plan a transition away from them. We become active in the climate movement, so the local climate guys here are CLEAN, which is the Climate Emergency Action Network of Adelaide, and they're a good group, so we join CLEAN. And then what we do is we publicly support activists. So when you hear your friends bagging out activists who have done an action, you say, well, hang on guys, this is serious, you know, we should be out there helping them. So that's what reasonable, sensible people do. They take out insurance. So thanks for listening. You guys have the power to make the change, so please do so.